Thank you for joining my talk today. My name is Dr. Ahmed Hala from Gaseous Electronics in Riyadh, Saudi Arabia. The title of my talk today is Nonlinear Dynamics and Intrinsic Chaos Regulation in Physical Plasma Engineering. Traditional plasma engineering treats deterministic chaos as an unwanted instability. The Hala framework proposed here changes this view. Chaos becomes tunable, programmable resource controlled by an intrinsic, state-dependent feedback operator, the so-called Hala operator. It's a mathematical operator that performs geometric quenching of strange attractors into stable states. Further, in actual Langmuir probe experiments, the probe plus plasma source system together does not use continuous voltage sweeps. Instead, discrete voltage steps on a concave IV curve naturally produce a recurrence bifurcation. This yields a clear, one-dimensional logistic route to chaos, period 4 bifurcation with Verhoeven's logistic curve-like behavior. Challenges in chaos control and limitations of traditional methods. Some traditional methods demand continuous real-time adjustments and precise knowledge of system parameters, yet others use excessive external damping, which introduces unwanted energy sinks. Some others, traditional controls, may violate natural conservation laws such as volume preservation and Hamiltonian-like flows, forcing the system into unnatural states that cannot be sustained in the long term. Assuming Hamiltonian systems is common in fusion, for example. So this is something that such treatments in this paper might mitigate and improve. So the geometric non-invasive chaos regulation via the Hala operator, which is shown here, it treats chaos as a programmable topological resource rather than an adversary effect. Instead of opposing chaotic behavior, this Hala operator harnesses its stretching and folding properties as a controllable feature that can be redirected toward desired stable outcome. It embeds an intrinsic coordinate-locked nonlinear feedback into the system stretching dimension. The feedback term is integrated into the governing equations, activating only wherever needed without requiring external forcing sensors or actuator for real applications. It operates autonomously by altering the vector field boundary geometry without external overrides. The operator modifies how trajectories behave at the edges of phase space, in particular, creating self-regulating containment while leaving the core dynamics untouched. The master equation of the Hala operator is just a regular 3D set of equations. It operates in the z direction, so it has a gamma quenching factor. This could be, function of time. It could be not, depending on the assumption. And it has this strong nonlinear term that actually both they control what happens in the z direction. And that's what it looks like. So that's the Hala operator within the bigger framework with the Hala attractor chaotic system, which we will explain down the line. So it introduces a quadratic, it's a quadratic quenching term, and the operator introduces state-dependent geometric folding centered on the target field line. This is a motivational analysis that I done a year ago. At the time, everybody knew that Lyapunov exponent takes extensive, so-called extensive computational work, but now it's easier done by the AI, for example. Or even though chaotic or chaos theory applications can be dealt with qualitatively, but from a quantitative point of view, the Lyapunov exponent is a metric that is standard when computation analyzes any chaotic system. So we did the computation, we published that in a pre-printed paper, and in the positive region, This is where the chaos sets in, and then this kick in when the gamma factor, this is the parameter, the gamma parameter quenches, kicks in, we move to the negative stable state. Now I use that with different autonomous canonical systems like Sprott A and Rossler. Rossler is a one-winged, simple, very simple host. It's one-winged, and you can apply the Hala operator with its quenching gamma factor, and this is what you get. I call that a switch. And then when I did it in a attractor, Sprott A, which is almost volume preserving autonomous system, Hamiltonian-like, I wound up getting a limit cycle. Both has applications. I use the protocol called successive controlled collapse, which we'll talk about now. We can do deterministic chaos compression via the so-called Hala SCC protocol. Again, these are the set of equations, differential equations. You find here our Hala operator term. It could be a function of time, done if you work on that. But then here also it's called gamma of t can be set to 0, and we can use it only as a simple, we set it to 0, and then we start integrating. For a certain value, when we decide to engineer the system so that gamma is on above 0, the quenching starts to a certain point. At other research that I did, I call it a stop bit in terms of information applications, but then the cycle goes back step by step, and I call it successive because it's one step after the other, controlled collapse. This is useful in programming applications, crypto communication, and also it is a way to predict what the system will do by engineering it. And there's nuances here and some other things that can be done with this protocol. When I apply this to an attractive system, I wound up getting a constellation of discrete points. So in reality, the SCC is the protocol to discretize a chaotic system. Some more information is found in my reference number 5 in this talk. Yet another system for control. This time is not intended for a controlled collapse where I get a discretized ending constellation. Rather, I'd like to have a reversibility. So I've done a few hybrid, I call them hybrids, and one of them has full reversibility, which is the one I am presenting here, the braiding one. I've done other stuff, 3D Hala. I took the Hala operator 3D, so it operates in the three-dimensional set of equations, and then this is the braiding system. And braiding is a technique known in dynamics to treat many dynamics problems. So that's what the braiding term looks like. And it did the preservation and shaping protocol, keeping the attractor going, compresses it into continuous manifolds while preventing total collapse. I call it here also chaos rescue, meaning the minute the system approaches losing its chaotic behavior, this hybrid can reverse it and bring it back to chaos whenever chaos preservation or chaos rescue is needed. Again, always you keep in mind the systems that can collapse to discrete fixed points, or other systems, simple hidden attractors like Sprott A, but then that get reduced to limit cycles. Both has applications. These are some computational diagnostics. I call them computational diagnostics. They're common nowadays with the AI engines. Before, going to the laboratory, we do design of experiment. We do design of experiment optimized simulations, whether multiphysics or particle in cell simulation. And I've done a few of them also in the preprints that I will present in the references. So that's a technique that's worth completing or pursuing, which is computational diagnostics. So you see here the braiding, two protocol locked in together, two attractors are locked in together in the phase space for the RN64. And this is passive Poincare section. That's Point section is passive diagnostic, common in chaos theory, but it's useful to decide on the timing, for example, if we're going to set the SAC protocols and so on. For such Lorentz host, again, you always use the Lyapunov exponent analysis to see what's happening. And these data are all computation can be done now much easier than before. It used to be hard to compute such data. I also experimented with the Sprott A. Sprott, again, is Hamiltonian-like. It will be very popular in the future for fusion reactions. For example, when Hamiltonian energy preservation is assumed. So this is the data, what it looks like. In reference 4, you'll find much more explanation. In the second part of the talk, we discuss the order complexity in quiescent plasma. Quiescent plasma, where do you find quiescent plasma? Q machines, for example. This is where it started. Thermionic multidipole plasma, classified as quiescent plasma systems where there is no apparent instabilities. You can study much physics there. However, I argued before that there is a qualitative resemblance between the Verhulst logistic curve and the Langley probe curve, qualitatively, after which I did some mathematical, investigation on the bifurcation of the Langley probe trace. It's important. It's important to look at it in conjunction with the plasma source. So the observed is coupled to the observing tool. In this case, the probe is used with such a quiescent plasma where no instability in the bulk is expected. So what do we find? First of all, these are the data of a normal, real-life Langley probe trace, and I fit it to cubic spline interpolation. These are raw Langley probe experimental, not computational data, but I just fit it to the spline for the sake of recovering the bifurcation behavior, which I got, and then did several studies which led me to believe that when coupling it to the plasma system, for example, sheath nonlinearity problems can be addressed. Others did that before, but they attributed any instability to actual instability present in the plasma. And all of these references I reference in at the end of the paper. So yet other people that spoke about non-manifest, this more recent, they spoke about non-manifest chaos. But in our case, we have this window of the mu basically in the bifurcation of the Langley probe, which we studied. And like I said, it's in the sheath nonlinearity without additional instabilities. I would like to draw a complementary diagnostics comparison between the Langley probe and the attractor, the Hala attractor. In the Langley probe trace, I do think that by now we should acknowledge that there is a logistic MAV recurrence equation associated with the Langley probe trace. This is useful. It reveals hidden nonlinear sheet dynamics invisible to classic theories, even in quiescent plasmas. So that's one application. The Hala operator on its part is a computational diagnostic that sets the stage for further experimental diagnostics. Okay, this is how it works. In the Z dot, again, you have the minus, and then you have this, basically the Hala attractor, which with its gamma quenching factor. More features, favorable features with the Hala operator that makes it attractive. I did study it in a preprint over 11 canonical attractor systems, and it proved a universality over these systems. So in that sense, it resembles what the Langley probe is doing. Langley probe spans a large range of density, electron density, and temperature, whereas the Hala operator basically can be validated across 11 canonical attractors. It is now, this is the issue of the Hala attractor as a standalone self-regulating universe. You can interchangeably call it a Hala attractor, or you can call it a Hala operator. And there is, it can qualify as an attractor in its own, basically. It does bridge the dissipative and conservative regime. It has universality that I spoke about. Industrial application in fusion, fundamental plasma physics, and some other applications. So this is the conclusion. This is the references that I spoke about, a few pre-printed here, some of which were used in papers that I wrote for peer review publication, which did eventually published. They got published, so the Hala operator is known at that level, and these are the other references. Thank you for attending my talk, and I'll be happy to receive your questions on my email, amhala@gazelco.com. Thank you very much.